So every type of mathematical object has its own category. So there's a category of rings, whose objects include things like the integers and the rational numbers and the real numbers, but then other examples besides. So I'm using notation that'll be familiar to mathematicians here. And any category, in addition to its objects, has some notion of transformation between those objects, which we draw using arrows. So these arrows represent the inclusion, for instance, of the rational numbers into the real numbers. The fundamental theorem of category theory says that any mathematical object, no matter how complicated, can be understood, can be characterized uniquely by its relationship to the other objects in its category. So for example, in the category of rings, you might think of the integers as being the numbers 0, 1, 2, -1, -2, together with the operations of addition and multiplication. But they're also uniquely determined by the property that in the category of the rings, there's a unique arrow from the integers to any other ring. So you can think of a category as providing a linguistic template for a mathematical theory with nouns and verbs. But as the objects mathematicians study get more complicated, you need a more robust linguistic template with adjectives and adverbs and so on. And that's the idea of an infinity category. So for example, there's a category of infinity rings. And like an ordinary category, this one has objects and arrows. So the examples have some different names. But in addition to the objects and the arrows, which we think of as being 0 and 1-dimensional, we have 2-dimensional arrows, arrows between arrows, that I draw in this way, and I think of as inhabiting a 2-dimensional space. And then there are also arrows between arrows between arrows, which we think of as inhabiting the 3-dimensional space, and arrows between arrows between arrows between arrows, and so on, all the way up. This gets a little bit harder to draw on paper. So mathematicians would like to use infinite dimensional categories, use infinity categories to help systemize their work in the way that mathematicians are using ordinary categories today. But the challenge with this is that it's very difficult to write down the definition of an infinity category. And in fact, there are many competing definitions, which means that when researchers are proving theorems about infinity categories, they have to first pick a specific definition. You can think of that as choosing coordinates, and then prove their theorems in reference to that definition. So this provides a translation problem. You might ask, if a theorem was proven using one definition of infinity categories, can be applied to an example of an infinity category constructed in a different definition. And even if that is possible, how exactly would that translation work? So this is the problem that I've been working to solve with a collaborator, Dominic Verity from Macquarie University in Sydney. And our approach is to apply the philosophy of category theory to category theory itself. So any type of mathematical object lives in a category. These infinity categories are very complicated objects themselves, but if we zoom out, we can think of them as living in their own category, the category of infinity categories. And the category of infinity categories has some particular feature, this universe in which infinity categories live as objects. We give it a name, we call it an infinity cosmos. So more precisely, each model of infinity categories defines an infinity cosmos. So if we prove theorems about infinity cosmoi in general, then they specialize to give us the theorems about infinity categories proven in absolutely every model. And this is a way to come up with a strategy for proving theorems about infinity categories that apply universally.